Okay, so 2018, number 3. So the graph of a continuous function g, the derivative of the function f is shown above. The function g is piecewise linear for x between -5 and 3, and g of x is equal to 2 times x minus 4 squared for x between 3 and 6. And there's the graph of g. Part A says if f of 1 is equal to 3, what is the value of -5? Of f of -5. So for part A, we have f of 1 is equal to 3, and I need to figure out what does f of -5 equal. Now, whenever we are given two function values like this, something like an initial value, and we're trying to find a new value, something that you need to think of is your fundamental theorem of calculus, which says that if I take the integral of a function, if I take the integral of a derivative, then I would end up with my original. Okay, so I'm given two values here, -5 and 1. So I'd go ahead and put those into the integral, and I would evaluate this from -5 to 1. So what we do is we're going to plug in 1 minus plug in -5. Now the derivative of f, it doesn't give us that, nor does it give us a function for f prime, but what it does give us is it tells us that the graph of a continuous function g is the derivative of the function f. So f prime is really g. So when I evaluate this integral, I need to be looking at the graph of g, because remember, an integral is either the antiderivative if you know a function, or it's the area under the curve if you have a graph. In this case, because I have it as a graph, it'd be the area under the curve. So I'm going to plug in some information that I know. I know that f of 1 is 3, but I do not know what f of -5 is. So I'm going to solve this for f of -5, and I think the easiest thing to do would be to move the f of -5 over to make it positive, and then I'm going to subtract the integral. Okay, so this would equal 3 minus, and then I need to find the area between -5 and 1. So let's take a look at this area between -5 and 1. So 1 and then to -5. All right, so let's break this up into some shapes. I've got a square actually here that I'll use. So that's a 3 by 3 square, so that's just 9. It's underneath the x-axis, so it'd be negative. The next shape that I would come across would be this triangle. This triangle is beneath the x-axis again, but it's 1/2 base times height, which would be 3. So this area is -3/2. And then for the next area, this is 0, so it doesn't affect anything. And then the next one is 1/2 base times height, so 1/2 times 1 times 2, which would just be an area of 1. So plus 1. So then 3 plus 9 plus 3/2 minus 1. And then simplifying this, 3 plus 9 is 12, minus 1 is 11, plus 3/2. 11 is 22/2, plus 3/2 is 25/2. Okay? All right, so for the next one, for the next part, part B, evaluate the integral from 1 to 6. So for part B, the integral from 1 to 6 of g of x. Let's take a look at the graph and see what's going on. Let me erase some of this stuff. So from 1 to 6, it looks like from 1 to 6 I have a box and then the parabola. So from 1 to 3 is just a regular area under the curve, and then from 3 to 6 is the parabola. Okay, so let's go through and break this up from 1 to 3. And then add on the area from 3 to 6. So the integral from 1 to 3, the area from 1 to 3, we saw it was a box. It was a 2 by 2 box. So that's just an area of 4. And then let's take a look at this integral for g of x from 3 to 6, and I'm going to do it off to the side here. The function of g from 3 to 6 is, and we can get this from the function or from the original problem here, is 2 times x minus 4 squared. You have a couple different ways of solving this. You could just FOIL it out and do some, you can FOIL it out and expand it and just do it, treat it like a normal polynomial. You could do a u substitution. A couple different ways of looking at it. Let's go ahead and do a u substitution just to kind of review that, what that would look like. So I would let u equal x minus 4, and du is just the derivative of this expression. So the derivative of x minus 4 is just dx, because the derivative of x is 1 and the derivative of negative 4 is nothing. So du is dx, so that kind of clears that up. And let's see here, the 2 and the squared would stay. So I'd have u squared du. The 2 would stay, and then I can change my bounds as well. So then u of 3 is 3 minus 4, which is negative 1. And then u of 6 is 6 minus 4, which is 2. Now, that may or may not help you because you still have to evaluate, or you still have to find an antiderivative of u squared, but it maybe makes the numbers a little bit smaller and less variables to work with. So maybe it makes it a little bit easier. So what we're going to do is we're going to add 1 to the power and divide by the new power, and then evaluate it from negative 1 to 2. Plugging in our bounds, 2/3 times 2 cubed minus 2/3 times negative 1 cubed. So 2 cubed is 8, so this would be 16/3 minus 2/3 times negative 1, 16/3 plus 2/3. So this 16, 17, 18/3 would be just that integral. So I'd have 4 plus 16, 18/3. Yep, 4 plus 18/3. Simplifying this further, it would be 12/3 plus 18/3 is 30/3, or just 10. Okay. Okay, so that's part B. Part C says for x between negative 5 and 6, on what open intervals, if any, is the graph of f both increasing and concave up? So for part C, increasing and concave up. Okay, so a function is increasing when its derivative is greater than 0, and concave down when its derivative is less than 0, or no, greater than 0. Concave up when the second derivative is greater than 0, or when the second derivative is, or first derivative is increasing. Okay, but everything needs to be in terms of g because that's what I'm given for my graph. So f prime is greater than 0 or g is greater than 0. F prime is increasing or g is increasing. So making the connection between f and g here, we kind of want to tie this together. So f is increasing and concave up when f prime equaling g is greater than 0 and when f prime equaling g is increasing. So I'm looking for somewhere on my graph where I'm positive and increasing. So positive would be above the x-axis. So it's none of this. And then positive and increasing. So this is positive and increasing. Positive and constant between 1 and 3. Between 3 and 4, I'm positive but decreasing, and then from 4 to 6, I'm positive and increasing. So the two intervals I would want to go with would be from 0 to 1 and 4 to 6. Okay, part D. Let's see. Part D says, find the x-coordinate of each point of inflection of the graph of f. Give a reason for your answer. Okay, so points of inflection are when, let's rewrite this out, of inflection occur when f prime changes from increasing to decreasing, or decreasing to increasing. So we're looking for somewhere where the graph changes from increasing to decreasing or decreasing to increasing because f prime is equal to g. So let's see here. Looking back at the graph, from -5 to 2 we're constant, so it doesn't change at -2. It doesn't change from increasing to decreasing or decreasing to increasing. It stays constant and then increasing, so that doesn't change anything. So this is not one of them. At -1, same idea, it's increasing, but then it's constant. It doesn't change from increasing to decreasing. At 0, same idea, constant to increasing. 1 would be increasing to constant, so that doesn't work. And then at 3, it's constant to decreasing, but that doesn't work. And then at 4, I change from decreasing to increasing. So that would be my only point of inflection. So I would say f has a point of inflection at x equals 4 because f prime equaling g changes from decreasing to increasing. So looking at points for this one, for part A, you would get 1 point for your integral, so some type of integral expression, and then 1 point for your answer. For part B, you would get a point for splitting it up between 1 to 3 and 3 to 6, 1 point for an antiderivative, so even though we did a u substitution, we would still get our point, and then 1 point for our answer. For part C, you would get 1 point for your intervals and 1 point for your justification. And then for part D, 1 point for your answer, 1 point for your justification.